So it's really a great pleasure to be in this workshop. All the experts are here, and I'm not really working in this area most of my time, so it's great to have some of the experts at least listening to what you have to say. So please feel free to comment and interrupt and so on and so forth. That's not the major theme of my work, and we would be very happy to hear any comments that you may have on this work. And I'm also apologizing, I missed some of your talks. I'm teaching a course with 450 students this semester, so somehow, I have to balance things. So I'm in statistics department, I also am in the CS department, and I want to do rigorous statistics. So rigorous, I mean in the sense of the 1920s or the 1930s. So what do I mean by that? I want theorems which have error bounds and on finite samples, like you do when you try to estimate the bias of a coin. I want algorithms that, I can say that they terminate, and when do they terminate, and what do they output. Ideally, this is not so much the approach of the 1920s and the 1930s. It's more the modern approach. Ideally, you would like robustness under the modeling assumption. So this is a very difficult problem, and I'm not going to say anything about it. But ideally, this is what we would all want, right? And we don't necessarily have that. And today, I'm going to talk about two initial steps in the area, in areas related to population genetics, for simple or two maybe oversimplified models. And both of these work are sort of works in progress. One of them is on the archive, but I don't want to declare it finished yet. And the other one is not even on the archive, so you'll see it. Okay, so I'm just going to say what the two works are. One is just something that we just put on the archive. So can one hear the shape of population history? So this should sound familiar to many of you. And the other one is optimal inference of incomplete lineage sorting, or incomplete lineage sorting. So what I'm going to talk about first, I'm going to talk about this question, which is, can one hear the shape of population history? And I'm only going to talk about population size, even though we have grand vision of how to solve the more general problem, which involves migration and so on and so forth. So this is joint work with Junyoung Kim from UPenn, and Mickey, who is sitting in the room somewhere, Mickey Ratz from UC Berkeley, and Nathan Ross, who was a postdoc here, and now he's at Melbourne. So yeah, it's like preaching to the converted. I don't think there's any point of even putting this slide. So we all want to infer past population size, and this of course has interest beyond population and genetics. You want to study species other than human, and it's really interesting to study the size and the history. So we know that. So now I'm going to try to offend the minimal number of people, including the minimal number of people sitting in the room, right? So we have a lot of work in this area. Many of the work in this area is in this room. So sort of if you want a very, very rough partition of the kind of information that you're using, you can use information about the coalescence time, and maybe a famous paper is the famous the paper of Lee and Darbin from a couple of years ago that essentially tried to recover population history from one haplotype. And there's a lot of work, both theoretical and empirical work, on using allele spectrum. So in particular, I don't want to get into the theoretical discussion, which is really interesting. So there's this papers of Myers, Pfefferman, and Patterson, which says that you cannot actually recover even the population size history from the allele frequency, but maybe you can under some assumptions and so on and so forth. So there are various people, including in this room, who have studied this problem extensively. I'm not going to talk about that. And then you can look at other kind of data, which is sort of blends of sequences that are common. And again, there's very nice work, for instance, of Rasmus here at Berkeley and others using this kind of information. So this is, for me, I mean, I don't want to offend anybody, but for me, all of this work is, maybe except of the work of Myers, Pfefferman, and Patterson, and the reply to this work, which are theoretical. The rest of this work I would call empirical work, right? Because really we don't really have very strong statement about, how certain are we of what we know in the sense of theorems. Any questions or comments so far? Okay, so I'm going to use the model of population that I'm going to use in this first part. We're going to talk about the history of the size of the population, and I'm going to use Kingman coalescent. So what we'll be interested in particular is the trade-off between the amount of information that we have, and I'm going to talk about which information soon, and the accuracy of the reconstruction of the history. So I don't know if there's any point of introducing the Wright-Fisher model or the Kingman Coalescent model in this workshop, but I'll flash the slides anyways, just so that you can look at them. And then I'll talk a little bit about what we know about that. Okay? So this is what I do for my students in situations like that. Detect the typo in the slides. Okay, so any typos, it all looks okay. Right? So this is the standard Wright-Fisher that we know. Of course, from the probabilistic point of view, the one feature that's important here is that the chance that we have more than two guys coalescing in one generation is of order 1 over n squared, so we can neglect it. So we can just talk about coalescence of pairs. And when we take the limit as n goes to infinity, what we get is we get Kingman coalescent. So this is a continuous time process where we go back in time from the present day to the history. And we know that the time for coalescence, when we talk about constant population size, we have these random variables that have exponential distribution with parameter k choose 2, where k is the number of individuals that we're looking at. Okay, everybody is very bored. Very good. Okay. So now let's make it slightly more interesting. Now we're going to look at variable population size. So it's the same setup, but the population size is changing. And the basic assumption here is that the population is well mixed at all times. So we want to apply the same variant of the Wright-Fisher model or the Kingman's coalescent model to this setup. So what happens is that what we have now is we have a random variable that at time t, the rate of coalescence is exactly going to be the same. We also saw it in other talks like Steve's talk yesterday. The rate of coalescence at time t is going to be essentially what it should be, k choose 2, but you have to normalize by the ratio of the initial population size to the current population size, because the time is always measured in terms of, we are not doing any time change, the time is always measured in terms of the initial population that we're looking at. That's the setup that we're looking at. Okay, so here's the setup. We have a well-mixed population. We have this function that determines the size at each time. And okay, now this is the point where I hope that you're going to shout at me. So please shout at me after I say what the assumption is. So we are going to make a very simplified assumption here. And the assumption is that we are going to have a lot of coalescence times of pairs of individuals. And the assumption is that they're going to be IID. Okay, so they're going to be independent and identically distributed. And this set I'm going to call T1 to TL. So of course, if you're not going to jump at me, let me jump at myself. Right? The obvious question is, where do you get this from? And my answer is that we don't really know where to get this from. We know how to partition the DNA into blocks. And if the blocks actually correspond to different genealogies, we can do that. But of course, partitioning them into blocks in an intelligent way is not something that we know how to do. But still, this is the assumption that we're going to make. And maybe one direction for future research, if we want to look at it, if we want to do something empirical, you can think about working in a setup where you guys provide some software that look at the DNA and breaks it into pieces and says, these are the pieces that correspond to different times. We don't integrate over this huge space of, the coalescence and all of the history. You are just doing some simple statistical method to break it down into pieces, and then we are going to apply some simpler algorithm in order to find out what the history is. So it's not clear if that's something worthwhile considering or not, but that's the setup that we're going to imagine that we're at.
I thought you were going to say something, criticize the word in orange or something.
You don't like the orange?
I know. I thought that was what you were going to say.
Oh, no. Right. So no, the other, you can also jump. This is a very legitimate. I'm throwing a lot of information away, right? So in some sense, I'm working in a situation where, say, I have just two individuals or one individual, and I'm looking at the two copies, right? So, but for me, this is very initial. Very aspects of these projects are very, very initial. Still, the amount of pain that we had in order to derive this result was enough for us to decide that we stop for now, right? But it's, as you see, the results are pretty simple. Okay, so what is the distribution? What is the distribution of the coalescence time? So this is something that we essentially saw at other talks before, including Steve's talk yesterday. So the probability that the coalescence time is less than the number capital T is given by this beautiful formula. So instead of simple exponential, we have exponential with the integral of n0 over nt. And what is the goal? Well, the goal is to estimate the population history, the size nt, from the samples T1 to TL. Okay, so we're all good? Okay, very boring. Okay, so now I'm going to continue doing something very, very simple. I'm just going to do the simplest idea that a frequentist would do at the beginning of the 20th century. I'm going to divide the time into intervals I1 to Ik. And I'm just going to count the data point in each interval, the number of coalescents in each interval of time. So that's what I'm going to do. So let's look at what the estimate is, actually. So hat xk is going to be the fraction of coalescence that I'm going to have at the case interval. And hat sk is going to be the number of all coalescence up to interval number k. Again, I'm going back in time. And here's the beautiful estimate. So maybe you're used to this kind of elegant formulas, but I'm not so used to it. So let's go over it slowly. So what do you get? You get that the estimate is going to be that the ratio between the population at interval k and the initial population is going to be the length of the interval divided by minus log 1 minus this hat xk over 1 minus hat sk minus 1. So why are we using this estimate? I don't know if this is going to help you, but the expression that's written on the bottom in the middle equation is exactly the empirical conditional distribution that we coalesce at interval k, given the fact that we haven't coalesced so far.
So the thing that n hat k is estimating is what the average of the population.
We'll get to that. We'll get to that in a second. Right. So we have to. Right, obviously, I want to. Especially again, if you can refer back to your talk yesterday, I want to, in principle, estimate something that's very continuous, but I break it into discrete intervals. So I have to say what I'm actually going to estimate. We'll get to that in a second, right? So. Okay, so again, what's the reason for doing that, right? So if you are very bored and you want to do algebra in the middle of a talk, what we're actually doing is we're inverting this equation over here. So if you ask what's the probability that we coalesce at interval k, well, it's the probability that we haven't coalesced up to interval k, and then we just use the formula that we've seen before. So we move this conditioning over here. We get this equation, we move the one to the other side, we take the log, and we get the equation that we have. Okay, this is just a very simple algebra. So everything I'm doing is very, very simple, right? It's too early in the morning to do anything complicated.
So it's the sort of thing that people in survival analysis, if they're wanting to estimate hazard rates,
right.
would do.
Right. So yeah, the difference with the kind of stuff that's usually done in survival analysis is that the people are looking for something smooth. And the estimates are, in terms of the smoothness of what you want to estimate. We are just going to ignore it. And maybe this is a very good comment, because in the setup of survival analysis, it does actually make sense to talk about smooth functions that we want to estimate, while in the setup of population genetics, we are interested specifically in events where, the population can jump very quickly, right? So maybe this assumption is not a very reasonable assumption. So one of the reasons that we're doing derivations that are somewhat similar to the derivation in survival analysis is that we want to consider a different setup where population can jump in a way, right? So, and we'll get to that, to the exact statements in a second. Okay? So we can provide a confidence interval just by using large deviation or Chernoff bounds. So let me tell you what these bounds will tell you. So first of all, we have to decide what is it that we're estimating at each interval. And the actual number that we're estimating, and this is maybe a very poor choice of name, is what we call the effective population size at interval k. And the effective population size at interval k is this expression. If the population size is constant, it's actually going to give us the population size. If it's not constant, it's somehow measuring something that's related to the rate of coalescence in the interval, which, if the population size was constant, would be given by this number, right? So that's the best that we can do somehow. Okay, so that's what we're actually going to estimate. And if you want to say what is the error, right? So the error composed of two terms. So this is the error that ideally we would want to measure. The error that ideally we want to measure, we would want to measure the maximal possible difference between the population size at the interval that we're looking at and what we estimated. That's what we would ideally want to measure. And of course, this error comes in as a sum of two errors. One of them has to do with how non-constant the population size is. So the error 1, the error for interval k of type 1, is just the supremum of the difference between the actual log of the population size and the log of this quantity that we're estimating. And the other term is the estimation error. So what is the difference between what we estimated, the quantity with the tilde, and what we call the effective population size in the interval. From people who don't like equations. Okay. Maybe you're not in the room. Okay.
Do something really pathological to get a big type 1 error with your concept.
Right. So very good. So that's a very good comment. So this error can be very large. And to some extent, once I've decided to partition the time into little intervals, there's nothing I can do about it, right? It could be that, there's some very, very crazy shape that's going on in this interval. And once I've decided to bucket the interval to that interval, there's nothing I can do about this. So this error, there's essentially no way for me to bound, except if I'm making some assumptions. Okay, so the smoothness assumptions, how many jumps, and so on and so forth. So in order to bound this term, I have to say, oh, if I make this and that assumption, then I can say that this quantity is small, right? But I cannot do anything other than that. Because indeed, if the population is crazy enough, there's nothing I can say about this quantity. So we will concentrate on the other quantity, which is the quantity which is related to the stat, right? So this is once I decided to partition into intervals, this quantity is just out there, and the only bounds I can derive on this are obtained when I make some assumptions about variations of the population. So very good.
Choose the sizes of your intervals.
Say again?
You can choose how many intervals and what size.
Right. So, but this makes some issues with dependence, which again, at this initial step, we don't address. Right. So that's of course a very good point. We don't address it at this point. Okay. So let's talk a little bit. Let's talk a little bit about the estimation error. So this is this difference between what we think is the effective population size and the actual population size. So for those of you who like equations, this is the beautiful bound that we get. Okay. So the probability that the log of the population size is in this interval, which I shift by log epsilon and 0. Again, the assumption is that the length of the interval is epsilon and 0. So the probability that I'm correct, I'm in this range between A and B plus this number, this is the form that you get in a Chernoff bound. So there's exponentially small error in C. And what is the interval? Well, the interval is this beautiful form from A to B, which includes the log of the log and all kind of minuses to make it very intuitive. Okay? So if you don't see immediately what this is, it's a little difficult to see what it is. So let me tell you a little bit about all of the parameters that are involved. So the most important parameter maybe is L, little l, which is the number of pairs that arrived at the interval that we're looking at, right? Because there have been a bunch of coalescence until this interval, and then there's the little l that is the number of guys that arrived to the interval. And then if we look at this quantity capital L xk over L, this is the fraction of coalescence inside the interval among all the guys that haven't coalesced so far, right? So this is sort of a natural quantity to look at. And if you'd ask what's the length of this interval, which is maybe of some interest, so if you actually calculate what's the length of this interval, assuming that L is not too small, and suppose you want to fix the confidence level to be 5% because you like to send your papers to Science and Nature, which for some reason believe in 5%, then what you'll get if you fix the confidence level, you'll get that the length of the interval is of order 1 over square root the number of coalescence that arrive to your interval, and then this quantity L over L xk, which if you think about it, this quantity before taking the -1 is essentially the length of the interval of time that you're looking at. So the length of the interval, the conclusion from that is of order 1 over the square root the number of samples, and then the inverse of the length of the interval in terms of time. So of course, there's some very deep insights that you all know that comes from that. That is that the deep history is much harder to recover, and short intervals, if I partition to short intervals, it's much harder. This is the way to quantify this somehow. Steve, you had a question?
I figured it out, thanks. Just give me more time.
Okay, any questions so far?
The reason you need independence is because you apply Chernoff bounds.
Yeah, of course. I mean, the reason I need independence is because I apply Chernoff bound. So you can apply this, and I mean, there are many future directions that you can go, including not using pairs and so on and so forth. But I just do the very, very simple, basic vanilla version of the problem. Okay, so this is how it looks like. So you actually, I mean, this is the nice thing about working with Mickey and Nathan. They actually simulate and see what you get. So you actually simulated this process. So what do we have here? I mean, let's look at this picture. What we have here, the blues are the actual population size according to which we generated the data. Okay, so these are the blue intervals. The little red intervals are our estimates. And the pinkish area is the confidence regime with 95% confidence, okay, or with 5% error. And what are the parameters that we have here is the number of pairs that we have here is pretty large. So in the top row with 3,000, the time intervals corresponds to 5% of the population size. So it's 0.05. That's the little intervals that we're estimating. This is with 3,000. This is with 30,000. You see that you're doing better, both in terms of the actual estimates and in terms of the error bounds that are a little smaller in this picture. Yes?
It's a little hard to see when it jumps from the top to the second blue line. Is it in the middle? Is there a blue line there, or is it off in the junctions?
You mean
to
here?
To the left of that, sorry. Left.
Here?
Little
Here?
for that. Right above that point?
Yeah.
Is
So here there's just the model is just
One-step jump.
the instantaneous jump, right?
Okay.
In one generation, the population jumped from whatever size it was to twice the size.
and that's where we get the errors, is in that jump period.
We get errors here, but we also get errors. We also get errors back in the history, right? We get errors in many places. But a very natural place to get an error is when your interval is not placed exactly before or after the point where the explosion happens, and then you're going to estimate something in between, right? So that's a very natural place for an error to take place. So here our error is actually outside the 95% confidence because there is this huge change in population. Yes, very good point. Yeah.
What's the difference between the left and the right?
So I think the only difference between the left and the right is it's just two different histories. Yeah, I don't think there's anything else. I mean, the top is 30,000, the bottom is the top is 3,000, the bottom is 30,000, but it's just two different histories.
So the bars there, your theoretical.
These are the theoretical bounds.
So if you actually done multiple simulations to sort of see.
Right. So instead we prefer to do one sample because it already shows that our bound could be improved if we are probably more careful. Right.
Okay, so
yeah.
rather than actually figuring out.
Right.
what the variable
Yeah, but you just look at it and you can improve these bounds, right? So, yeah. Yes.
What do you assume about the size of each locus? What's the mutation rate?
Right, so so this is of course a very important question, which I'll get to in a second. I actually make a very strong assumption here that I have the exact coalescence time. Okay, you provide me with the exact coalescence time, and I provide you this picture, right? So it's like, of course, I said it's a very idealized model, and I'm going to talk a little bit about that. I'm going slower than I wanted. Okay, so how much time do I have, by the way? Now that my estimation procedure.
I have 20 minutes more.
Okay. Yeah.
You said you could improve the bounds, but
Right.
like the intervals where your confidence interval goes all the way to the top,
Right.
I would guess that that's where you don't have any data. Like,
Yeah, of course. Sometimes you cannot improve the bound. If there's no coalescence events, I won't use this word online, but you're dead, right? There's nothing you can do, right? It's like, if there's no coalescence coming into the interval, if all of the process coalesce, then, this is why you have often you have this one-sided error, right? So this would not improve all of the way, but it would improve in some of this regime. Yeah, that's a very good point. Yeah.
It looks like the bottom left, after the second change, your estimation improved compared to before that. Yeah.
So I'm not sure. I mean, right?
I'm
So
sorry, the third change jump.
right. So I'm actually not. I'm not sure that
Not there, a little to the right.
here.
A little
The
more.
next change.
Here.
Yeah, so it goes from very broad confidence intervals to.
Right, so I guess this is just the fluctuation. I mean, so the bounds here are actually sample dependent. Right? It depends how many samples arrived at this interval. So we are not averaging, right? So there's some randomness in the process, which, depending on how many events arrived at the interval and how many coalescences actually took place, the width of the interval will change.
The population got smaller there.
Right. There were more events. Somehow around here, there were more events of coalescence, somehow randomly, and that's the reasons that the interval was small. That's a very good point, yeah. Okay, so let's look at another example. I mean, you can just stare at it. This is a case where there's both a jump and a more smooth transition to the population size, and that's the picture that you get. So it's a similar. Okay. So what did we get from that, right? So as statisticians, what we want to understand is, one of the things that we want to understand is the width of the interval, the right width of the interval. So what we said is that essentially we can think about this width if the interval is of length epsilon, and as long as L is large enough, then the width of the confidence interval for a fixed confidence level is going to be epsilon over square root L. It's going to be order of 1 over square root L. And on the other hand, you can show, or we can show that using the data that we're talking about here, you cannot see smaller differences than that. So let me say what do I mean by that. So let's look at a bunch of pairwise coalescence time for population of size n. And let's look at another bunch of IID pairwise coalescence time for a population that's a little bigger. So these are, both of these populations are constant size. One is of size n, and one is of size n times 1 plus a. A is a small number, right? Think about one fixed population and a little bigger population. Maybe I have a picture here. So what do we know? So, okay, maybe everybody here knows what the total variation distance is? Steve knows. Is there anybody who you should know? So the total variation distance between two distributions tells you what is the statistical distance between them. Right? So if the statistical difference is small, you cannot distinguish between the two distributions. So what you can prove that the total variation distance between the coalescence time that you will get from a population of size n and the population of size n times 1 plus a is order of what? Is order of the difference, the fractional difference of the population size times square root of the number of coalescence that you're seeing. Okay, so it's the square root here, and the square root here corresponds exactly to the square root here that we've seen before, right? Because in our model, when we're looking at some deep interval, we are looking at only those pairs that haven't coalesced up to this time. So this little l actually corresponds to the big L. So it means that the width of the interval is indeed of order square root L, right? So the conclusion here.
So here n is just constant. The population size is constant, is it?
Right. So in order to prove that what we're doing is optimal, it's enough for me to show one scenario where you cannot do something better than that, and then one scenario is a very simple scenario. I mean, you can think about this interval as some interval way back in time. So there's some interval way back in time, and I promise you that this interval is going to be either of the size of the initial population or 5% more. And I'm telling you, can you tell me if it's the original size of 5% more? And this result tells you that if square root L times A is much smaller than 1, is approaching 0, then you cannot do better than random. Then you cannot do better than 1/2. Okay, so that's the setup here. So it means that at least in some sense, if you look at the width of the interval, up to constants and so on and so forth, the procedure that we presented is optimal. So you cannot get a confidence interval that's smaller than order square root of L, 1 over square root of L. Okay. Any questions so far? Okay, good. So here actually, this is something that I've never seen done in papers, but we decided to do in our paper. We actually draw 3 things. One is the actual population size. This is again in blue. The red. The red is our estimate, and the black are the two populations that we cannot distinguish better than with 95% probability. So if we had this fixed population or this fixed population, we cannot distinguish them with probability, with confidence higher than 95% probability. Here, it's, the intervals are shrinking and shrinking, and what we're showing in comparison is our actual estimates, right? So this is just to give you a visual view of what are the results saying. Okay.
Why does the black and the red bars not? Why are the black lines inside the red bars?
Say again?
Why are the black lines inside the red bars?
Why are the black?
Because I would think if you could distinguish the two with 95% confidence, then they should just be like a bar width apart, right?
So the actual population size is here.
Right.
And I cannot, it should typically be the case that the red bar is between the black bar and the blue bar, but not always.
I think he means the confidence interval, the pink bar. Why is the pink bar and the black range not the same?
Not the same. Okay. So that's a very good question. So the pink bars and just because these are, if you want to talk about this 1 over square root L, this is where the constants come into the play, right? So it's not the same constant, right? So this if you look at these pink bars, then the pink bar are some much bigger constants, so you see a very, very big difference between the two, right? So there's a factor of, if you look at actual data, our bounds are not optimal in the constants, so you lose a factor of 2 or 3 or 4 or 5. I don't know exactly, but you lose some factor. Yeah, thanks.
But the black line is just for the red, the dark red line should fall in between the black lines.
No, the black bar, yeah, maybe, okay, so maybe the reason we haven't seen this figure before is because it's confusing. So let me try to explain this figure. Okay. So there's 4 types of data on this figure. Right? There's the actual population size from which we generated the data, that's the blue. There's what we estimated, which is what the red. There's the confidence, the 95% confidence interval, which is this pink big bar that we've seen before. And the other thing is that what our bounds are saying is that in order to distinguish with probability better than 95%, given the amounts of data that we have here, we have to have two populations whose distance is at least the distance between the population here and the population here. This is the last result. In order to get a 95% confidence, it has to be, the population difference that we have to exhibit is at least the difference between the two black populations. We can talk after the talk, there's a few other things I want to say. So, okay, so, right, so going back to Yoon's question, so what we really want is we want to work with sequences, and I'll just summarize what we know about this very quickly. I'll skip this slide, and I'll skip this slide, and I'll say our bounds are not very good in terms of, if you look at finite sequences, what do you have to do? So when I talk about bounds, I talk about two directions. One direction, maybe if you give me finite sequences, then I can apply standard tools and say, oh, the actual coalescence time is going to be in this interval with high probability. This is just estimating a binomial random variable. So I can do that, but it's not clear. We don't really understand how does this affect our estimation procedure. And also our lower bounds, when you use sequence data, do not match the upper bounds right now. So I think one interesting research direction is to extend this kind of work when you actually look at sequences. And this is actually something that I'm going to talk in the second part of the talk for this other problem. So let me move to the second part of the talk. So this is what we've seen so far. So we have a simple method. We understand the bounds very well. It's for idealized data somehow. I think one very natural question is, what do you do when we have to work with finite sequences? And of course, it would be really nice if we could work on real data. So if we get some finite blocks from some of you that you believe in strongly enough, and you get coalescence time that are accurate enough, you'll be very happy to do that. So let me talk, at least mention in the last 10 minutes, let me mention a work with Sebastian, which actually does deal with the sequences. So Sebastian work is over here. And so this is the question about population trees versus gene trees. So who wants to hear about population trees versus gene trees? Or, I mean, in the sense, who haven't seen this before? Okay, so I have to say something about population trees versus gene trees. So this is a speciation tool for subspecies, but when you think about the species, there's actually some thickness here that comes from the fact that there are actual populations here. And what can happen is that if you look at a specific gene, well, this is the species tree. When you look at the gene tree, what will happen is the coalescence of the gene is going to take place in a different order. Right? So if you look at this tree, we have this pair, and then this pair, and then they meet over here. But if you look at the gene tree, what happens is that these three guys meet first, and then the other guy joins them last. Right? So somehow the genes and the species don't have exactly the same tree. And this is a well-known problem. And about maybe 10 years ago, Degnan and collaborators noticed that assuming that all the genes coming from the same tree, or taking something like majority tree, is not going to be a consistent way of estimating the tree in this situation. So this is something that is done for a while. So one thing that was also mentioned in one of the talks, so it's a very easy observation, but maybe we were the first one to make it, I don't know, is that if one estimator that you can take for the distance between two populations is you can take the minimum over all the genes of the distance or the time of divergence between the genes for these two populations. So that's a very natural estimate. And you can show that this is a consistent estimator, and you can even show very simple upper bounds. So if you use this to build a tree, I'm assuming a molecular clock here, what you will get is that you will get that the probability of any error in the tree, assuming that all the gene trees are correct, which is again a strong assumption, the probability of error in building the tree is going to be at most the number of population that you have times something exponentially small in the number of genes. But how exponentially small crucially depends on C, which is the shortest branch on the tree. So somehow short branches are very hard to detect. We know that in phylogeny for many years, but it's the same phenomenon in population genetics. You have to somehow get to the short branch in order to be able to detect what's going on there. Okay, so this is a result that we had with Sebastian about 7 years ago. And interestingly, in the paper, we said, you should not use this in practice because this is not very robust. And then a few years later, papers started showing up saying, we tried this in practice and it doesn't work. So, we didn't really know how to react to that because the paper said you should not use this in practice because this is not very robust. But anyway, people were complaining about it. So, and they didn't cite us for this complaint because we complained about it, right? They should have cited us for. Okay, and there are many other methods for linear sorting that people develop after that at about the same time, so I won't go into that. Let me just mention the result that we have with Sebastian. So what we know is that if we have sufficiently many accurate gene trees, then we can reconstruct a population tree. We also know just by standard arguments, assuming that the model is correct, that if the gene is long enough, then the gene trees are accurate. And the question is how long, how should we set up the parameters in order for this to work? And what we proved very recently, actually, essentially here at Simons, is we know everything, right? So we know how everything scales. So if f is the length of the shortest branch, then and k is the length of the sequences, then the number of genes that you need is exactly given up to constant or logarithmic factors, actually, by the maximum of 1 over the shortest branch length and 1 over square root the length of the sequence length times f squared. So this is assuming standard mutation models like Jukes Cantor and so on and so forth. Okay, so this is again related to the question that Yun was asking. For this kind of model, we don't know the result just with the ideal coalescence times. We can actually say what the results are in terms of the sequences that we need. So in particular, if the number of genes always have to be at least 1 over the smallest branch length in order to get something correctly. And then the length of the sequence that you need is this expression, which maybe is not completely natural, is 1 over the number of sequences squared and 1 over the shortest branch length to the 4th power. So there were various special cases, especially the 2 endpoints of the interval, where m is equal to 1 over f, and when k is equal to order 1, which this was done before, so I'm not going to talk about that. So, right, so I said already all of that. So I was planning that if I have some extra time, I'll tell you what's the intuition for what's going on. So far, the paper is 25 pages. I don't think I'll be able to do it in 2 minutes. So maybe I'll stop here, and I'm happy to take more questions.
Why is this the hardest case?
Right. So let's draw the picture here. So you have this very short branch here, which is of length f. And somehow I have to decide if these 2 populations meet first or these 2 populations meet first. So in order to distinguish this case, I have to have enough events where the coalescence actually occurred in this short interval, and I actually have to I don't really know that it happened in this interval, right? Especially if I have sequences, right? I have to, somehow my statistical power has to be strong enough in order to say, well, it's more likely that in one scenario, I'm not working with coalescence time, I'm working with sequences. The sequences that I have indicate that I indeed had a little bit more coalescence in this short interval. So that's somehow the hardest case to distinguish. That's the story.
So in real life, you've got to break up your genome into sufficiently large enough chunks that the coalescent trees are independent of each other, or have different coalescent trees.
Right, so I think... Sorry, go ahead.
So there's less of a problem on the length of the sequence, but there is a limit on the number of genes there are actually in the genome for which you can do this.
Right.
There's a limit on n.
Right.
And have you any idea, just in terms of numbers, whether this actually could work?
So I think it could work in some situations, it probably doesn't work in other situations. I think one lesson that I would hope that some of you may take from this lecture is the lower bound, right? So our results are optimal. So if one of you is saying, oh, I'm reconstructing this very beautiful species tree from this data that is, I have these sequences of this length and I ran my method and I got something, this result are saying, you cannot do it with confidence if you're below the bound that we stated. But of course, the other scenario is also interesting. I think in some situations, definitely people have reconstructed, species tree from gene trees that seems very, very reliable to me, right? So as far as I can tell, maybe not to you.
If you run PSMC on a data set, then you get like this posterior and decoding set of coalescence times. Might be interesting if you put those into your method, you could compare your confidence intervals to like the runaway behavior of PSMC inferences and like see how close they get to your theoretical lower bands. I guess
I'd be very, very happy to talk about it, and if somebody does it, right? As a theoretician, I really like that people, are considering this kind of question and sort of gauge the gap between practice and what you actually use. Yeah. And we can talk about that later. I'd be very happy to talk about it.
No more questions? All right, let's move on to our next speaker.